Yeah, it's like, seeing right now. Okay.
Okay, if you're ready, you can start.
All right. Thank you all for being here this morning with us. My name is Charlie Schinke.
I'm Clark Group.
Shopka Diapro.
I am Joseph Bell, or Joel B is fine too.
And we're here to talk to you about our senior design presentation so far. So a little intro to our project. We are tasked with creating a system for the automatic controls lab in which students will be able to experiment with magnetism and controlling a closed-loop system. We're in charge of creating the infrastructure so that students in the future will be able to take use of that to further their learning. More specifically, the course title is MEC 4310, and we're tasked with creating a system that uses magnetic levitation via attractive force as opposed to repulsive force in the heave or vertical direction. In addition, we are in charge of putting together a complementary software package in MATLAB and or Simulink so that students will be able to use that as the interface to control the system. The system has to use closed loop control over the vertical distance to control the distance between magnetic components. We have a cost constraint to keep our entire system and project under $1,000, as well as a volume constraint due to the setting in which the system is going to be used. When we were first tackling this problem, we had a bit of trouble trying to figure out our system sizing when it comes to magnets and magnetism due to there being distance as a variable. Equations that you might be familiar with in physics classes become very hard to implement and use in order to predict the actual behavior of your system. Because of this issue, we sought help from a couple of professors, one being Dr. Massoud and one being Dr. Faulkner, who both guided us along a more experimental approach. So keeping that in mind, keeping our cost in mind, we decided to purchase a few magnets and some other simple materials to get some information on how our system might actually function, get some data, and then use that as kind of guide rails for furthering our ideas as they were developed. We came up with a couple sketches as well as some 3D prototypes and some experiments turned into physical reality, as you might see in front of you. If you're unfamiliar with maglev or magnetic levitation, it's becoming increasingly used in the application of high-speed rails. The basic premise is that you balance weights or other forces with magnetic force to reduce the actual contact between objects and therefore reduce friction. And obviously, if you don't have friction, you're able to accelerate things much faster. You're able to get things to go at higher speeds with less force. And the magnetic systems require a closed loop control because these magnetic systems are naturally unstable, meaning you won't be able to find an equilibrium that satisfies your need or goal. You need to be constantly detecting the state of the system so that you can correct it. If you're unfamiliar with closed loop control, or maybe you haven't taken automatic control systems yet, this is a basic block diagram of what a closed loop control would look like. You have our input. For us, that's our desired vertical position, and our output is the actual vertical position of our ferromagnet. And then using a sensor, we detect that output and then weigh it back against the input. Based on that difference or that error, that goes to our controller. In our case, we're planning on using an Arduino, and the controller outputs a control effort based on that difference. And then obviously with disturbance, such as friction, fluctuation in the magnetic force, that all goes to our actuator, which is our electromagnet, controlling the actual position or controlling the output of our system, which is our ferromagnet.
So now let's jump in a little bit to how we went through our design process. So initially we had to come up with some design requirements, which included being able to operate using the MSOE supply system or power supply system in the auto controls lab. It would also need to be able to amplify and reduce the nominal force from the magnet using the coil current in the electromagnet just so we're able to increase and decrease the distance in between ferromagnet and electromagnet. And the temperature obviously needs to be regulated because we are using this in an educational environment. And if the current running through the coil causes the coil to reach a high temperature, it could be potentially dangerous to students who are not as educated, as they have not taken the auto controls lab class yet. So now, how do we start our design process initially? Well, there are a lot of unknowns that we need to figure out, such as how strong our engine is going to be, the carriage weight, and the friction that will be seen in the system. So first, we wanted to make a test stand in the form of a frame to try to figure out how to characterize these unknown issues and figure out the magnitudes of them and be able to figure out ways to combat these issues. We then started the frame construction, but then we paused it to prioritize the magnetic characterization and maglev prototyping. As you can see here, our prototype table. So here's a picture of our early test stand and what the knowledge that we gained from this test stand was. We initially wanted to go with a 2-axis design, which would include both the vertical and the horizontal directions. We then decided that due to a few faults in this design, we wanted to go back and simplify it a little bit and stick with only the vertical direction of movement. As the beam on the cross section between the two poles will significantly increase the weight of the carriage. We're also seeing some staggering in between the poles, which increased the amount of friction and broke the parallelism of the entire system. And with this design, we also wanted to switch to ceramic coated aluminum rods instead of just. So how do we define our port of entry for this project? Well, some of our theoretical limits, as Charlie mentioned a few slides ago, this project would be almost impossible to do with theoretical calculations. So Dr. Masood was very helpful in guiding us to a more experimental routes. And from there, we could create a calibration curve for some of our unknowns that we need to identify. The force characterization is the only variable from our project that cannot really be guessed, but rather be selected by a choice of a magnet, which we made a variety of purchases and of different magnets to try to figure out this force characterization. And so our project is a data-driven design, and the port of entry made it so that the frame could be built around the measured capabilities of our project rather than just assumptions.
So, as mentioned before, we don't really know how to begin the project unless we know some type of forces that permanent magnets are providing, as well as the electric coil. So we need to come up with an experimental device that will be able to measure both permanent magnet strength and the electrical coil strength. This photo, you see the names of all the components that I used, and I'll briefly describe them all. So it's basically a lever system with a frictionless point right here. Ferromagnet sample suspended right there, and the weight distribution going to the scale. Moment balance provides you with a simple equation to get the actual magnetic force. And the benefits of this setup is the fact that we can adjust the wing nuts to get a very, very certain distance in between the magnets, between the samples. Additionally, we made interchangeable tips to see the effects of the coils and magnets on different sides of ferromagnetic materials. Yeah, here you can see the equation that was used. So simple sum of forces and moment of the pivot points. The good side is that this whole lever system only had 580 grams or so of weight acting on the scale, which left us about 1.5 kilograms of weight that we could have used to fluctuate. So that's good. The scale was set to newtons, which gave us the right answer in newtons for our forces. Then we started thinking about how to design the electrical magnet that would be able to incorporate some kind of a permanent magnet on top of that. The original design that was the inspiration was gotten from basic electrical magnets that do not use any permanent magnets. That design, it has both angles going this way, which helps the magnetic flux conduction to get focus direct on where we want to do. But it wasn't necessarily very practical for us to mount that, considering how the frame would look like. So we decided to go with the second design, just the cylinder with the coil wrapped around it, heat sink on top, and in the bottom you see that there's a threaded hole and we can vary the number of permanent magnets attached. So first design, we used a core from 1018 cold rolled steel, 3/4 of an inch in diameter, and wrapped it with 19-gauge wire. Here we were able to see that we actually produce good amount of magnetic force, but we also learned that for us to transfer more of the magnetic flux into the system, we need to match the diameter of the core to the diameter of the permanent magnet. This was smaller than the diameter of the permanent magnet. This produced a good amount of magnetic force, but it would overheat quite easily. Second design, where we made the adjustments for the diameter of the core to be close to the diameter of the permanent magnet, but with a little bit of a cutout. So when we when we wind the coil, it would nearly become a cylinder. Here we also attached a threaded hole for the permanent magnet. Here we noticed a very, very significant increase in force. And we used the same diameter wire as well as in the small one, which was 19-gauge diameter. But we've noticed that the overheating was a really, really big issue here, and we needed to deal with that in the second iteration. The final iteration, which is mounted right here. Here we used a much, much finer wire, which resulted in significant increase in number of turns, which in result increased the ampere turns, and that is the ability to generate magnetic force around it. Here we've noticed that by putting a cooling fan right there and stripping all the heat from the coil as well as the heat sinks in the bottom, we're able to test and experiment a little bit longer, but still a little bit more work needs to be done over there. The inside of the coil, the inside of the core is also isolated with a capped on high temperature tape in order to prevent the shorts acting onto the frame, which would result in eddy currents as well as just short and losing all the power that we needed for that coil. So yeah, the baseline design was selected to be the third iteration of magnets, where the core matches the diameter of the permanent magnet, as well as much finer wire is used. At this point, we can safely say that in the second semester, the team can be split into refining the motor as well as building a frame based on this design of the motor, because it provides sufficient enough data to elevate weight more than we actually need.
Yeah, so now I'm going to talk about like our actual test procedure. We've sort of been building up to that, and that was our main sort of conclusion for this semester, right? So following this, we have, as you can see, these different ferromagnets, basically just pieces of metal attached to the pieces of plastic that we would mount in here. And then we had different permanent magnets, some of which you can see are attached to our different electromagnets. And what we would be doing is we pair these different magnets up and essentially see how the force changes as we get closer and closer and closer between the washer and the magnet, right? So this is our air gap distance. That's what we were varying. And then the force is what we were recording. And we did that both with our first ferromagnet, changed the different permanent magnets, and then reiterated that same process with each other washer. Okay, the next one. So once we introduced the coil, things got a little bit more complex. The first thing that you're not seeing on this slide is our preliminary tests adding current in just to see what the coil would actually do. And as Shab mentioned, initially our force variation due to the introduction of the coil was really, really small, right? And we needed a way to boost that up. So once we finally got to this design that you see here is where we made this matrix of the current and the force, and then, the current and the distance and the force that we got out of it. Yeah, you can keep it there for a bit. So diagram up there of what that would sort of look like. This is essentially saying that we picked our main permanent magnet and we're not really sure what our washer is yet. But we still have at least our selected permanent magnet to go with our electromagnet. In terms of what this table is trying to get at, some of the values are definitely a little dubious. They don't necessarily establish a trend, but that's because these are our nominal distances. So when I was measuring this, especially when you're doing it manually, since the system is so unstable, it's tricky to be like, oh yeah, this is exactly 5 millimeters or exactly 10 millimeters. So it might be a little bit higher and a little bit lower. And another thing I noticed is that depending on just the orientation of the washer next to the magnet, if you're maybe off center or too close to the center, that will also vary the force a little bit as well, right? But in general, what we were noticing, and this would be a fairly decent example of this, is as the current is negative, we see that there's a reduction in force because the magnetic field generated by the coil is going in the opposite direction. And then once we get to zero, it's about the same as if there was no current. And then here, we're getting these 24 measurements because our scale is literally maxing out in terms of newtons, right? But obviously, it's still increasing. That's about it for this. We can sort of keep going here in terms of our things that we're looking to do for next semester. Is we need to find a sensor with a fairly fine resolution, right? So we're looking at least a 0.1 millimeter resolution. Ideally, even smaller would be great. And it needs to be compatible with our software package. The other thing is finally finalizing our main configuration with our electromagnet, permanent magnet, and washer. And that's going to be based off of the sensitivity of the system. We concluded that if we have a larger sensitivity, essentially a larger range, that would be better for us because we have more ways to vary the current and get both subtle and large changes in the force. And then also the force to weight ratio, because what that will do is give us the nominal distance, essentially our starting point, right? So if we're thinking about just static equilibrium, what's our force to weight ratio, that being the magnetic force and the weight of our washer, are balanced, that's where we can start. So just to sort of give you a picture of what we've sort of completed in our feedback control system, we essentially have our actuator down. We might need a little bit more fine tuning, but that's our electromagnet. What we're looking into next is figuring out what the sensor is and the controller, and the system we have almost nailed down in terms of what our washer / ferromagnet is. We just need, again, a little bit more deliberation to figure out exactly what we're looking for. That's coming from our force to weight ratio. Go ahead. So another thing that we have to actually do is develop our Simulink or MATLAB model, right? And in order to do that, we understand that, our system is already internally unstable, right? So we would want to do our automatic controls math, essentially, to figure out with our root locus where it can be stable so that you can actually go back really quick. That way we can pick our controller, set our gains so that our system does in fact become stable. Keep going. This is just essentially our final product at this time. Go ahead, keep going. That's what we have. I'd like to send our appreciations to Dr. Faulkner, Dr. Masood, Dr. Wang, of course, for guiding us along this journey as well. And also the EE department, because we stole like, I don't know, maybe a few miles of wire. So that's what we have. So feel free to let her rip with the questions.
All right, thank you. We'll take questions from committee members, guests, and our audience.
So could you go back to your control diagram? What are you envisioning as the disturbances?
Something that might not have explained super clearly is that our intention with our ferromagnet is to have some type of guide as we control the vertical direction of it. So some friction with that. Also, just some imperfect or non-ideal factors with our ferromagnet being not perfectly level, the magnetic attraction not being evenly distributed around all of its volumes. Things similar to that, just kind of non-idealities, I think, is what we're anticipating.
So does the output from the controller and the disturbance input at that summing junction make sense? On a unit point of view,
From a unit point of view,
engineering units?
I guess not so much. I don't think this is our so much like the concrete. We're riding and dying by this graphic. This is more just for the purpose of illustrating the concept of a control system at this time. Yeah, so I guess from the point of view of units.
So when you analyze it, you need to have units that are consistent. So typically the disturbance comes in between the actuator and the system because of that. The actuator is producing force, right? And the force and the disturbances you list, or some of them you listed sensitivity issues. But if you listed friction, then that would be driving from the actuator. That would be placing that summing junction between the actuator and the system.
Very good enough. Thank you very much.
When you come to model that, that would be important.
One question. For the controller, how did you tune the parameters like the gains?
We have not determined that yet.
Okay.
We're not sure exactly. We have not. That's a part of the project that we have waited to dip into because we were uncertain on exactly a lot of the information that we deemed necessary that would allow us to get to that point. So we're unsure at this point.
You can go back to the table for the results. I see the trend is changing from as you're increasing the distance. So basically, it would be good to show it in like in a form of plot to show the trend. And why the trend is like there is a like optimized distance or something that the force drops. Like the last column, the force is dropping as you increase the current, right?
Oh,
What is
yeah.
the reason?
So, yeah, like I said, there were just like, when I was doing these tests and whatnot, I'm doing all these measurements manually. We had like a dial caliper and whatnot. So I'm fairly certain that this point is just a junk point, but in terms of our time frame, it wasn't something that I was going to be able to like retest. Something I might even end up doing over winter break. Is that sort of getting at here? Yeah. Yeah, we're well aware that some of this data just does not illustrate the trend that we're trying to get there, but based off of our other tests that we have, we know that this is useful as we get more precise.
The questions from audience. Okay, yeah, thank you very much.
Thank you.
So the next group can get prepared. We have. I think we have 7 minutes for you to prepare. So, but if you're ready, you can start. You can start.
Should just be able to plug into this thing, no problem, so.
Yeah.
Oh. See. On time. Right now, so that is Vegas. So it's all good.
H.
That's good. Uh, so if I do this, that means you have 2 more minutes to wrap up. All right. If you're ready and want to start, you can go ahead.
So good morning, everyone. So we are the ankle foot orthopedic design team, a team of our computer engineering student and mechanical engineering student. And my name is Wilfried Tapsoba, and I'm a computer engineer major. And I have
Nathan Wilde, I'm a mechanical engineer.
Chidibel Chadwick, I'm a computer engineer.
Braden Roth, I'm a mechanical engineer.
So what's our problem? Traditional ankle foot design is sometimes required like the patient presence for physical prototyping, and it's required like multiple feeding, which cause some delay in the treatment and delivery. And additionally, we have like the patient behavior, especially children, when they have some problem with their feet and we try to get them an ankle foot orthopedic, they sometimes are reluctant to try it on. And that causes like some issue like doctor trying to get them to try on, delay negotiating with them. And that's like too much delay into the time to get that done. And on top of that, people suffering with some issue with their feet, they want to be able to walk properly later. So our goal is to be able to provide an ankle foot stimulator that can ease the process of the design and eliminate some of those multiple meetings with doctor to come up with like the feeding. So what's our solution? Our solution is to develop a simulator to capture the biochemical and anatomical data and enable remote design and optimization of the patient's specific ankle foot orthopedic. And what's the process? Basically load like the patient data into our simulator. We run the simulation, and with that, we'll get the design parameter and capture those biomedical data, and the patient wouldn't have like to be there physically. And at the end, with this data capture, the design can be able to design a specific one that will fit properly to the feet of the patient, even if they didn't do like a multiple trial. And we hope like this will help people gain the property to work properly without like having some issues and without having to see the doctors multiple time. And to be able to get to this result, so we start with some background research to gather some information to see what's already out there and what we can learn from different design and be able to get our simulation. So the first background research article we find is on the design and manufacturing selection of our ankle foot orthos. And this article provides like a comprehensive survey of the current state, the different method used and requirement to develop an ankle foot orthopedic. Although we are not developing one, it was good for us to know how it's developed so we can better run our simulation and develop our goal. And from this article, we learned the different 3-point pressure and improve gait function of the patient. And these 3-point pressure that they use in the design are the proximal posterior calf, the foot sole, and the dorsal foot. And the characteristic property of in this paper we found was the stiffness, and this one is based on the patient weight and the type of deformity, which we also take into consideration in our simulation since different people have different weight and different feet. The deformity of their foot. The geometrical shape also varies from patient to patient. And as you can see here, those are type of example of ankle orthopedic that's already exists.
So then we decided to look at it like generally what is biomechanics and gait data and then gait analysis. So biomechanics is the study of how the human body moves. It involves aspects of physics, mathematics, biology, chemistry, physiology, and human anatomy. And then we did research into the walking cycle itself and found that it consists of 2 main phases, the swing and the stance phase. During the stance phase, the leg is actually on the ground and the other leg is the one swinging. And then once that leg comes up, it's swinging. And then obviously the other leg stays on the ground. And then we found
just an article on gait data itself, and we found that it has 4 main categories. Anthroparametric, which has to do with like the patient's physical attributes like height, weight, body mass index, stuff like that. It also has spatial temporal, which is time and distance, so walking cycle, speed, step distance, that kind of stuff. Then obviously it has kinematic and kinetic, which are dealing with position, velocity, acceleration, both linear and angular. And then ground force reaction, which is when the force that the foot experiences when it hits the ground. And then that's used to kind of figure out the internal forces within the leg. And then on the right, this picture here is kind of a picture on how gait data is taken. They use these infrared markers placed on the patient at specific points. And then they have infrared cameras around the lab. And then the patient just walks through the walking cycle. And then that takes frame by frame. And then from there, they're able to get position data, stuff like that. And then in order to get the ground force reaction, they typically use force plates on the ground and then just have the patient walk over the force plate, and then they're able to get a measurement from there. So then next we're going to look into, we decided to look at some studies that analyze gaits. The first one used a real-time visual feedback in order to try to improve gaits of patients that had experienced a stroke. And they used this hip attachment that you can see on the right in picture B that would go on the patient's leg. And then they would have the patient just walk in a treadmill, and then they had these glasses that they put on, and it displayed this image at C. And then so if they were in the right hip extension angle, they were able to get, it would show up green, like saying they were in the range. And then using that, they were able to improve, I believe it was walking speed. No, walking speed was not statistically improved, but the hip extension angle was. And this kind of just showed us how gait data is analyzed, taken, and also a study that improved gait data. The next one was a smoothing spline analysis of variance models, which basically was just a different way to analyze gait data. This source honestly only provided gait data for us that we could use in our later simulation, which I'll talk about later. But it just looked at a different way to take data and then also analyze the data, which made it easier to see imperfections in the patient's gait data.
So the next thing that we were looking at was current mechanisms in the market for length adjustment of the links. We determined that it'd be very necessary for us to use length adjusting links because it would help replicate the person's gait data better. The first one that we found was mechanical taper jack, which is actually a patent that I was able to find. As you can see in figure 1, it shows the mechanism that they use to raise and lower the actual like trailer. It also attached to the trailer, but that's not the component we were mainly focusing on. It was mainly the mechanisms inside, which would provide a 90-degree angle from the crank to the screw, which would help raise and lower it. As you can see, there's kind of custom parts. More research was used to find out that like there's also worm gears that can be used, which translates the 90-degree torsional force as well. It's just a little bit more simplified than the mechanisms used in that one. Motorized desk legs. We're also looking at electronic components to see if we could use that to adjust the legs. The article was about obviously mechanical motorized desk legs being raised and lowered by linear actuators and motors. You can see in figure 2 over there, that's the actual linear actuator motor system that they would use. They'd take an input signal from the controller, and then that would control how much it would raise and lower.
The next one that we did was like to find the actual design that already exists, and this was an interesting article that we did look on and see what people already did. And this article was the phases, design, fabrication, programming by one of the professors at the university. And on this one, they used like a robotic system to kind of simulate the walking cycle. And the ankle foot simulator and the ankle foot orthopedic, like the outfit. And for this mechanism, the complex robotic system is responsible for the orientation of the foot in different phases, which was like provide some insight information into how we can it right to our current design of the ankle foot simulator. They use the mechanically hinged ankle joint paired with an electromechanical locking system to control like the motion of the leg. But we are not like controlling of the motion, we want to get like the data. So we kind of see like how they did it on the end and how we can improve in our end and develop our own simulation.
So our design is driven by several key objectives. One is to accurately capture the kinematic and kinetic data. This requires high fidelity sensors to measure two distinct types of physics, one being kinematics, which is like the geometry of motion. This involves joint angles, velocities, accelerations, and then kinetics being like the forces and torques that are present, such as the ground reaction force. And then this is vital in determining if the orthosis actually corrects the patient's gait. The next is gait data conversion. This is essentially be able to take the input data from the patient and then using equations and algorithms to then convert that into signals for the voters to replicate that motion. And then next is accommodating different patients. As mentioned before, this is the adjustability of mechanical structure in the form of adjustable links to accommodate for different patients with different heights and therefore different length proportions. And then simulating a patient's full gait cycle without the orthosis just demonstrate the control and then provides a direct before and after to see if the gait's improved. And then the constraints are that position accuracy. So essentially the difference between the commanded position and what the actual position is, we deem 5% to be sufficient here. Weight limitation, we don't want any unwanted inertia, so therefore lighter materials like aluminum are more ideal. And then the budget limit just limits our manufacturing and using off-the-shelf parts if we can.
So our first proposed design was the one seen in the picture right there. As you can see, marked by the blue, there's adjustable segments for the upper and lower leg. There's position sensors located at the knee, hip, and foot. There's motors at each joint. So the ankle will have a motor, the knee will have a motor, and the hip will also have a motor. And then there's also be a force sensors at the bottom of the orthosis. So the orthosis would go on the actual foot, and then there would be ground contact force being able to detect like the ground contact force with the force sensors. There'd also be a frame to hold the entire thing, as well as bone outline of the patient's leg.
So then for the second mechanical design, it's very similar to the first one. The leg would sit in this frame. The frame ensures that while the simulator is running, there's no kind of like wobble messing with the data. So this will ensure smooth motion. There would be a motor at each joint, and in order to properly replicate each like knee, hip, and ankle joint, there would be a force sensor grid on the bottom in order to detect the ground reactive forces of the foot while it's walking. And then it would be necessary to make not only the segments adjustable, but then the frame, so then we can get the correct hip height from the ground. And then the shape of the top link wouldn't matter too much. The bottom link would most likely want to be shaped like a foot in order to properly fit in the elbow, along with the possibility of adding foam to the lower half of the middle segment for the same reason.
This is like the first design concept for our electrical circuit. This features a programmable microcontroller in the form of an Arduino board. We chose this over like something like an STM board just because it's easier to interface with different peripherals and there's more availability for external libraries. This features flex sensors, which will be put at each joint to measure the joint position. Force sensors at the bottom of the foot to measure the ground reaction force, and then DC motors to drive the motion. And then a breadboard is used just for easy reconfigurability and then testing different components. And then this is our second schematic, which is like the evolution of the first one. This features motion sensors in the form of the MPU 6500 chip from TPK and Vinsense. It's used to measure gyro and acceleration. This requires I2C or SPI as output communication protocols, and we chose I2C just because it uses fewer pins. It allows multiple devices to be connected easier, and the speed at which it needs to run is more suited for sensors. This requires pull-up resistors, usually around 4.7 kilo ohms, that are connected to the operating voltage, which would come from our microcontroller. And then these must be connected in parallel, which means on the software side, we need to use addressing. A multiplexer may need to be used to add further addresses. And then there's also dedicated controllers for each motor. So the microcontroller would send the step in direction to each controller, and then the controller would send the appropriate analog signals to the motors, which will drive each joint. And then the Flex C4 sensor is connected to the analog and digital pins on the microcontroller.
So our final design is kind of a combination of everyone's designs, because we all have pretty good ideas. Again, we have a frame, or likely an adjustable frame, so we can match the link lengths and the height differences. Again, adjustable links, we'll have those, so we can match the proper link segment lengths of each person, as those can vary depending on person to person. Position sensors, just so we can know better accurately replicate the person's gait, helps us a lot. Force sensors, we ended up deciding on it being on the bottom of the orthosis, because then we can get the ground contact force, and that would also help us. And then an adjustable foot plate, because each person's foot shape and size is different. So having that as an adjustable feature would also let us fit the orthosis better, which would also better ground reaction force, and hopefully simulate better on the actual orthosis itself.
And then once we came up with the final design, we decided to move into proof of concept to ensure that we could take gait data as an input and then replicate the motion. So to start, we're going to use this anthroparametric chart you can see on the right. This is purely used for determining each link length segment length. It is based on like ratios of the patient's height. And so the ones that we care about are obviously the ones on the foot, the 0.53 times the height, that kind of stuff. And then we decided we needed to determine the inverse kinematic equation used to calculate the joint angle. And it basically just uses the two positions of that segment to determine the angle. Then once these angles can be seen, obviously we were going to use that diagram there. Once these angles are calculated, they can be not transferred, but adjusted to fit the motor inputs. And then we weren't entirely sure if we were going to be getting gait data based on the patient's like joint positions or the center of masses. So if we are this is based on if we're getting data on the patient's joint locations, but they can obviously be modified if the center of mass positions are given as well. And then from there, we took the sample data that was from the second research article, and it came in the form of joint angles for 10 patients walking under 3 different conditions, which was unbraced, a brace on the knee, and then an ankle brace. And then also gave joint data for both legs, every single joint. So then we kind of filtered through, got one patient unbraced and only focused on one leg. And then we were able to put this data into MATLAB. And then we use that data we use the MATLAB script to then perform a Simulink simulation, which can be seen here. So this just kind of proves that we can take the gait data from a real patient and then replicate their motion in order to best run the simulation.
This is the plan that we have for our development process. Our first phase is just further to put the 3D models so that they're ready to use. And at the same time, we're setting up the software environment, which includes just developing the level grinders and then just including any external libraries that are necessary. Next would be CNC work mainly, and then further developing those program modules. And then the final step of assembly is actually putting the mechanical parts together and wiring all the electrical components. And then at the same time, finishing the main program flow of sending the controls to the motor, sampling data, known times, and then converting that data. And then lastly, just debugging, testing, and auditing.
So bill of materials, based off our research on current products or the possible costs of components we need, we found out that the mechanical components would be $570. This includes the link adjustments. Electrical components, $225. Just differently, breadboards, parts, motors, everything. Miscellaneous components and prototyping, $100. We want to make sure we had room to prototype and also test our product. So.
And so our next steps would be obviously be building the actual simulator, but then we would need real patient data. So we would need height of the patient or use the leg segment calculations. And then we'd obviously need the linear positions to do inverse kinematics and then transfer that to joint angles. And then we would also need the kinematic data, specifically the ground reaction force, in order to determine if when we run the simulator, if the gait is improved or not. And then that data will then be output into like a spreadsheet, and then the doctors can look at the simulation results and determine from there as well. That's all we have for today, so we will take any questions now. Thank you.
Yeah, let's first take the questions from the audience.
Yeah, so I guess I'm just curious what the division of labor is between the computer engineers and the mechanical engineers.
Yeah, so right now it was very heavy on the mechanical side just because all of the research was based on the mechanical side, but then obviously second semester we're actually building it. So obviously the computer engineers will handle the controls and the motor stuff, and then mechanical will handle the actual leg mechanism and then the framing as well.
The lengths of the leg really the only dimensions that are of concern when constructing this, or is there other factors that go into like sizing for this, like the circumference of the leg or things like that?
Our main concern was just the lengths of the leg, because we assumed that like obviously every patient's going to be different. Like on a Jurassic end, you could have a child and then an adult, and they have like crazy changes in the leg lengths. And then if we don't have that adjustability, we can't properly like replicate their gait. We didn't really care too much about the circumference of the leg because it was just based position wise. So does that answer your question in a sense?
More so about how you guys gonna approach the speed of each element of the leg. So you can't, like, for example, if the person is walking faster, you have to accommodate for the motor speed for each of the links, right? And stay within those 5%. How are you guys planning to make sure that the leg just does do that all the time, you know?
That would probably be on the controls end, but I believe within that gait data that we get the time of the walking cycle as well. So we can try to adjust how quickly the motor goes from position, because the input's going to be the position angles. And it's just going to be like an array of data, and it's just going to keep going. Then we can adjust the timestamp from there.
Okay, so not necessarily controls with gains, but rather go through data.
Yeah.
Like from some of the articles, there are like some locking mechanism that they use, and I can prevent it to go like all the way like lock it, but we are not like going to one like using like locking mechanism. But that's like something that can be implemented, but just looking like normal walking cycle based on like the data that we get.
Okay, how many degrees of freedom are there in your system?
Do you mean like the actual like movement of the leg?
Yeah.
It would just be 1 degree. We're not really looking to see like different like angle bending or different stuff like that. It's just like a single like motion.
So you have 3 joints, right?
Oh, yeah, well, yeah, all right, yeah, there's 3 degrees.
We're only really focused on the movement in this plane, not necessarily
Yeah,
anything in this plane.
That's,
Well, what about the contact? According to your simulation, is there a contact happening or it's just swinging?
And the only contact is when it reaches the ground.
Okay,
the main thing being simulated is the actual gate. It's not specifically the ground contact or ground reaction.
so you're just simulating one cycle. Like,
Yeah, just the walking cycle.
and you're saying you're using inverse kinematics or inverse kinematics to figure out the angles. The first question is how do you, in the first place, get the absolute position of those joints? What sensor do you use?
Could you repeat the question? Sorry, okay.
2 parts. The first part, how do you get the absolute positions of the joints? Because you use arctangent X and Y, so how do you get X and Y? Those are absolute position.
Yeah, that is going to be what's given to us through the gate patient data. So we'll be given, if you can go back to the biomechanics slide. Yeah, the research one. This one. So these are what is giving us the position. And so while this is like they obtain the gate data, they will have markers on like down the leg, and that's where they are getting the absolute positions from. And then that's going to be the gate data that we're going to be given from of an actual patient.
Okay, and second part, you're going to calculate the theta values, the angle values.
Yeah.
And then you said the motor input will be a like function of those angles. What's the function? Meaning, how do you design the controller such that the motor can be controlled based on the theta?
Mechanical side, I don't know too much into it. I was just told that they would need inputs of like what angle they need, and then they would like program that. And so do you want to answer that question?
Do they have much?
Once we get like the data and know like where the position is, and we can just like say like how we want like to control, because we have like model like each of the joint, and then we can say like how we like the pressure that we need like the motor to manage, just like the raising that or bring it down basically until the movement from and same for like the sensor that we have there to like give us like this position and even real time where is the patient leg at this real time, and based on the position that we get, we can now control that what we want to do that, what we want to go like up, down, or like something like that. So kind of, you get what I'm saying.
I get what you're saying. So, what kind of controller,
What kind
control
of,
algorithm do you have?
we have like the so this would be like the secret that we have over here with the Arduino breadboard. That would be like our main controller that kind of control the sound now.
Yeah, what's the algorithm? What code do you deploy to your controller? Is that what is that algorithm? I know the control will be done by the board.
It's just using like a Arduino program like C++ that we coding.
The control algorithm, I mean, is that PID? What kind of like state space? The inputs are the angles. The output is something related to the motor. How do you map the input to output?
We just need the position of each given time. I'm not sure I get like what your question. Can you make them rephrase it?
Wait, what do you control?
What do I control? It's the movement of the leg. Once I get the position, I can just like control to use the motor to either raise it up or break it down.
So you control the motor.
I'll program the Arduino board to control the motor based on like the position given basically.
Okay.
So he means what's the algorithm that you use? Like is it PID control or what? Maybe you can answer.
Could you, or they don't work like PRDs?
do you use the PID control or like other algorithms you have in your mind based on your literature review? What the control?
The motor specifically, they just need like a step and direction, so like just based on the angle, it'll define the step, and then just depending on what phase of the walking cycle we're in, will be the direction, so.
I think maybe, like, what's the math that gets you from the input data to the output? Like, what goes on in the brain of the controller so it can know how to operate?
I mean, the whole process is that we take in the position data, put it to the inverse kinematics, and then we're able to get all the angles of each joint throughout the whole walking cycle. And then from there, that data kind of gets inputted into the control side of it, and then it outputs replicating that each angle to like each time step of the walking cycle. And then from there, we're going to compare the position and the ground reaction force that we take during the simulation to the unadjusted, like they call it an abnormal gait data when the patient has a deformity or walking but they just don't walk in an normal sense. Probably not the best way to put it. And then we're going to compare the simulator's gait data to the abnormal one and see if there's an improvement or not.
All right, any other questions? Okay, thank you very much. Good one. And I think our next group can get prepared. Well, actually, we have 3 minutes. Do we want to wait for Dr. Lisa a little bit?
I saw him walk in.
All right, yeah, let's just wait for 3 more minutes first. Let's wait for 1 more minute.
There's one.
This is supposed to start at 9:15 probably.
In his office, I'm assuming, yeah.
What does HAFO stand for?
You'll learn all about it.
Oh, all right, all right.
Almost angle, but more.
Yeah, I'm tired.
All right, you can get started.
Good morning, everyone. Thank you for coming to our presentation. My name is Abby. This is Katie, Austin, and Enzo, and this is our hinged ankle foot orthotic project proposal presentation. So our project statement is the goal of this project is to develop a hinged ankle foot orthotic for medical patients, specifically those with foot drop that control foot positioning, plantar flexion, and dorsiflexion. The device will incorporate a locking mechanism designed to unlock consistently from heel strike to mid stance and remain locked through the swing phase.
So moving on to more about foot drop and what the condition is. So foot drop is a condition where a person has difficulty lifting the front of the foot in the upward or the dorsiflexion direction and while they walk. And it's actually not a disease, it's a symptom, and this results from nerve damage, muscle weakness, or neurological conditions causing the muscles in the ankle to be weak or not functioning properly. And instead of smoothly clearing the ground as they're walking, they kind of end up scraping their toe or their foot along the ground as they're walking, causing it to drag, also causing their body to have to swing their leg outward or lift their leg higher than normal, which causes pain if they walk like that for a period of time. So more about the gait cycle and kind of what we're looking for in treating foot drop. So it's problematic because, again, it disturbs the normal gait walking mechanics. And the altered walking pattern increases the risk of tripping and falling, especially on uneven surfaces or stairs. And it places extra stress again on the knee, hip, and lower back joints, and over time it can cause joint degeneration. So more about kind of what this is the gait cycle, and it shows one complete step from the moment your heel strikes the ground to the next. And the first 60% is called the stance phase, where the foot is on the ground the entire time. So even from when the heel starts touching the ground to when the toe is lifting off the ground. The remaining 40% is the swing phase, where the foot moves forward through the air. This is the more crucial phase that our orthotic has to make sure it keeps the foot in the upward or the dorsiflexion direction to make sure that foot isn't scraping against the ground. So to treat foot drop and help gait mechanics and walking, you can use an ankle foot orthotic device. And there's two different types that we've looked at, the SAFO, which is the solid ankle foot orthotic, and the HAFO, our hinged ankle foot orthotic. And the solid ankle foot orthotic is great at treating it as it holds the ankle in a steady position, but it really limits the movement in the plantar flexion or the dorsiflexion directions as the ankle is held in the same position. Whereas the hinged ankle foot orthotic allows for a lot more motion and more of a normal walking gait.
So this is a project that a team last year started that we are taking over. Last year's team designed a hinged ankle brace that could actually lock and unlock through the patient's walking. The idea was to use sensors to detect when someone is walking and lock the ankle. The main problem was that the brake just wasn't strong enough. So the ankle experienced more force during walking than expected, and the brake couldn't reliably hold the foot in place. On top of that, there was a built-in spring that was pushing against the brake, and that force was not accounted for in their calculations, so it was acting against the system. Finally, the sensors that detected the walking had delays and connection issues, so we weren't really getting real-time data. And because the ankle would sometimes lock, sometimes slip, and sometimes not work at all, which ultimately led to its failure. And so this is the orthotic that the group last year made, and I'll pass it around to you guys for the locums. So last year's objectives focused heavily on sensing and measuring things like measuring joint angles, detecting gait cycles, and collecting kinematic data. Those are all valuable, but through testing, it became clear that the main limitations was not sensing, it was mechanical reliability. As you can see on this slide, most of the objectives describe the device and what it's measuring rather than its physical behavior during walking. That made it difficult to ensure that the brace could consistently perform its most important function, which is supporting the foot through the gait cycle. Because of that, our team refined the objectives to focus the device on not what physically does, but what can be measured. We kept the core safety requirements such as biocompatible materials and smooth edges, as these are non-negotiables when it comes to a medical device. The biggest change is that we shifted from measuring motion to actively controlling motion. So our goal is now to reliably control plantar flexion and dorsiflexion, which directly addresses the foot drop issue. We also separated the locking behavior into two clear requirements. The device must unlock during key strength to mid stance so that the user can walk naturally. And it must stay fully locked during the swing phase to prevent that toe drag. Finally, we need to make sure that the HAFO can fit in a standard shoe as patients will be wearing this throughout the day. It needs to fit the shoe. So last year's design constraints focused on broad systems like total weight, cost, temperature, and general locking performance. These constraints were important for safety and feasibility, but they were largely high level and just generic. So as you can see on this slide, many of these limits don't directly describe the real forces or physical spaces the device is experiencing during walking. Because of that, the constraints didn't fully prevent the main issue that we saw, which is the locking mechanism wasn't working while the patient was walking under realistic loads. Similar to our objectives, we refined the design constraints, getting help from Dr. Liu, Dr. Rizza, and Tom Current from Hanger Clinic. Our updated constraints are more specific and more realistic. Instead of generic force limits, we now require the locking mechanism to reliably activate under 110 to 120% of the user's body weight, which reflects the actual load seen during the gait cycle. We replaced the general weight limit with a system level constraint required to total orthotic weight to be no more than 2 pounds. This ensures that the mass is controlled where it matters most, which is around the ankle. Rather than simply stating that the ankle must be maintained, we now define performance in terms of torque during the gait cycle and the swing phase, ensuring the device provides enough resistance to prevent that toe drag. Finally, we decided to add a strict volume constraint to ensure that the locking mechanism fits within its physical space as well as the user's shoe.
So there were some previous design issues, as you guys may have noticed when playing around with the brake. The first one is the drum material. It was made out of TPU, and this was really flexible when you would squeeze it. And there was also a lot of wear on the sides, as you can see in this video. And then the brake geometry, the positioning of everything on the brake. So the drum, the lever arm, and where the solenoid is kind of off. So it got to the point where only the left side of the lever arm is touching the drum. So the positioning didn't maximize what was actually being contacted. And then the solenoid, so right here, this is the plunger that I'm pushing on. The stroke length of the plunger is inversely proportional to the force that it produces. So a shorter stroke length means much larger force. So this can definitely be moved closer, so we could shorten the stroke length.
I'm now going to talk about our 4 conceptual designs. We really did a lot of focus this semester on the actual braking mechanism because, like Enzo just talked about, if the braking mechanism isn't going to work, then the circuit doesn't really matter, the solenoid doesn't matter. So the first one we looked at was actually the same design or type of brake that last year's group worked on, the short shoe block brake. As you can see, it's pretty simple. It consists of a lever arm on top with a brake pad on the underside of the lever arm and then a drum. So the lever arm is pinned on this schematic on the left side with the actuation force, which would be produced by the solenoid on the opposite side. And the idea is that when it activates, it just pushes down and the drum stops rotating due to the friction between the drum and the brake pad. So our next 3 designs are all different types of band brakes where essentially there's a drum that's pinned at the center that's free to rotate, and there's a band that wraps all the way around it and is connected to a lever arm, either above or below it, just depending on the design configuration. This is the simplest type. This is a non-differential band brake. It's a non-differential because, as you'll see in the next slide when we talk about a different design, this one consists of the drum, the band around it, and there's a lever arm where one end of the band is pinned at the where the lever arm is also pinned. So that makes it a non-differential brake. This one's good because it has less linkages, so it's smaller and therefore more compact, cost effective, and most likely easier to manufacture. Kind of building on from that, this is the differential version. Pretty much the only difference is this differential linkage length S here, where now instead of the band being pinned where the lever arm is moving, it has its own pin at the end of the differential linkage. This makes it so that a higher torque is produced with less actuation force. And as I talked about, this would be a little bit more complex to machine or manufacture. But a pro about this is that it can be self-locking where less actuation force is required, and friction will essentially take over and stop the entire device from rotating. And our fourth design, we call it the vertical band brake. I say we call it that because, as you can see, the other three designs, those pictures came straight from engineering textbooks. This is kind of a design that we kind of just came up with on our own that doesn't have concrete equations associated with it. And the major difference between this one is you can see the lever arm above the drum. It's not pinned, it's more of on a track. And the idea is that the solenoid would pull up on it and the tension from the band would then stop the drum. For scale, this isn't concrete yet, but the diameter of the drum, which is also on the orthotic that we pass around, is roughly 1 inch. So you can imagine how small these tracks would be on the backside that the lever arm is going up and down. Really hard to manufacture, probably pretty weak and easy to break. The other problem with this would be that the alignment would have to be very precise because if the arm is getting pulled up, if one side's going up faster than the other, it's the tension and friction is going to be off, and it's probably going to ultimately fail over time. So we put all four of those designs into a decision matrix. It should be noted that the more points or the higher score that design gets is the better. So as you can see here, these 6 categories, they were pretty much just based off of our design constraints and objectives. The two most important categories that we discussed as a group was the efficiency under load, basically turning that actuation force into the so that the drum would stop rotating and the ankle would be able to lock, how efficient that was, and the size, because as you can imagine, the patients that would be wearing this this orthotic already have trouble walking, so the last thing that they need is a huge break on their ankle that makes it even more difficult. So as you can see here, the two best designs that we determined were the differential and the non-differential band brakes. We decided to move forward with both of them because although the non-differential got the best score in testing, which Enzo's about to talk about, it will be very easy to switch back and forth between the two, basically just changing where one end of the band is pinned. If it's pinned at where the lever arm is pinned, or if it's pinned on the differential linkage, changing the type of brake.
So when we get back from break, we will be doing some friction testing with the two designs. And the goal of this is to find an accurate coefficient of friction and then to also size the solenoid that meets our requirements. So we're going to test multiple geometries, which I'll show. We're going to measure the forces that are being applied on each end of our bands. And then we're going to move forward with an aluminum drum. And then we're going to test multiple bands, which with an aluminum band, some leather bands, and then zip ties. So this is our schematic. We have the brake drum here, the bands here, and then we're gonna hook on springs that it hooks on both sides. So the spring is gonna hook into each end of the band, and then it's gonna hook onto these pins right here. So we can easily just unhook it and rehook it to have different geometries and different setups. And then we'll have our weight here, and this will also be unhooked, so this can go from one pin to the next. So to stay in like our control volume, we decided these dimensions. For this dimension A, we're going to do 0.75, 1, 1.25, and 1.5 inches. For C here, we decided 0.25, 0.5, and 0.75 inches. And then for the forces we're going to apply, It's gonna be 10 pounds to 30 pounds, in intervals of 5 pounds. And then these are the equations that we can use to validate what we're seeing and what we're measuring. This equation, once we have F1 and F2, which we'll get from the springs, from measuring the displacement and the spring constant, we can also measure theta, which is the wrap angle. So essentially, from the center, what the angle is produced where the band stops touching the brake or the drum. And then we'll have all these, we'll know F1, F2, theta, so we can easily solve for mu, which is the coefficient of friction. And then this is the same thing, except for this differential linkage, just adding more geometries and testing different setups. And then this one's different because we have another parameter, which is C1. So the A and C2 are the same from before. C1 is going to be 0.25 inches and 0.5 inches, again, to stay in our control volume. And then F will be the same as well. So for this brake, we have some different equations, including the torque. And the max torque was given to us by Dr. Liu, and that turned out to be 33.9 inch-pounds. So we don't want to go over that. And then again, we can use this equation to validate that what we're seeing and measuring in our test is accurate. And then we can use the same equation as before to measure the coefficient of friction. So this is our project plan for second semester. We're hoping to come back from break with everything we need ordered and delivered. And then we're going to do the test that I just described and then purchase a solenoid that will meet our requirements. And then we're going to take a closer look at the circuit that's set up. There already is code for it. And that was provided by a software engineer last year that helped out with the team. So we can talk to her and see what she thinks. And then from that, if there's any issues or we need to order any other instruments, order those. And then we're gonna, once we have all that set up, we can model this on CAD because we went to see Tom Current. We got Austin fitted with a new one. So we have that file, that CAD model, so we can print mounts and design mounts onto an actual SolidWorks file. And then we'll troubleshoot any issues that arise. And then we'll have the final prototype and finish up our report and final presentation.
So here's a general anticipated budget we have for this project. And we split it up into mechanical and electrical components. Then mechanical is our friction testing materials, so the boards, screws, our types of bands and springs, as well as miscellaneous materials as the device is in a shoe. So we have to get a pair of shoes and a solenoid, and then other circuit materials, so our wiring and sensors. Then this is kind of a summarized budget where our total project cost is about $558, which is good because it's underneath our $1,000 budget.
So then a big thanks to Dr. Rizza, obviously our advisor. Dr. Liu gave us great insight on objectives, constraints, and specs for our project and what they should be. And then Mr. Tom Current, who we were able to go with his clinic, and like Enzo said, he took a hold of my lower leg. And so we are eventually going to get our own plastic mold for our project because that's the mold that last year used. Any questions?
So let's first take all questions from the audience.
So I guess just a clarifying question to separate your group from them. You guys are making like the end product and they would be making the system that like recommends to the doctor the product that should be given. Yes, no?
I believe so. You guys are making something that's going to test the orthotics, correct?
Yeah. The simulator that you go to check. Okay.
Yes. And then we're just designing the orthotic that's going to prevent patients from having foot trauma.
So your orthotic could be tested by their machine.
Theoretically.
Gotcha.
We have had zero contact with them.
Wow.
Yeah.
Nobody's been asked, how would I ask?
All right, so you had, in your constraints, you got I didn't notice it before, so sorry, I missed it. But you have 0.25 to 0.33%. Is that a typo? It's in your report too.
Yeah, that was something that was given to us and that we decided when we met with Dr. Leo and Tom.
Yeah. I think he gave you the maximum torque.
Yeah.
Which is 30, you guys say 33.9 huge pounds, but you're maintaining 0.25% to 0.33%. Is that a typo? 0.25%.
That's low.
Seems low. Yeah. Should it be 25 to 33%?
Yes. Yes, you were incorrect. I wrote it wrong.
It's a typo.
Yeah.
Okay.
Yeah.
And then I don't know if 25 to 33%, it might be itself might be low. He can comment on that. What his opinion is.
I think well done, the groups, right? You provided in detail for the pros and the cons. Very good. So yeah, I had a similar questions about that because I remember in class, Tom, Clarence, and I gave you the normal torque, the range, right? From 0 to the peak. I think the peak is for the typically developing children is about 1.2 or something, 1.25. It's a little bit needed, like per kilo, right? It's very high. So I think it corresponds. Yeah, correspond maybe, as you said, 33.
Yeah, we converted it.
34, right? Converted. I think, yeah. So then when I saw 0.25%, I think maybe just 5 inches. But anyway, great job.
But it's 25% low.
I think that the 25% back, that's another, question. It depends. How do you justify that? You have all peak, right? So you can choose 25%, maybe add it on another 50%. So it's experimental. I don't know how, what is the right number at the beginning, because you need the numbers to test it.
Yeah.
What do you think? Even 25%? 25.
Quarter of the total.
Quarter of total. So it's
Okay. Well, why don't you guys think about that? See what, we can talk about it again when the next term.
I remember you guys mentioned a temperature constraint. I think it was 100 degrees. With ours, it's pretty easy. We can just have some fins on there, put a fan in front of it. How exactly do you plan on, if that becomes an issue, handling that?
Yeah, so that temperature constraint was from the group last year. We did not proceed with that temperature constraint in our list of constraints because we're just gonna, I guess, see that in the test and then see if that's something that we actually need to worry about. But just from our knowledge, we're kind of assuming that that temperature is going to be so low that we're going to be able to neglect it. But when we test it, we'll actually be able to see if that's something that we need to worry about. And if it is, then we'll go from there.
It was also brought up by Tom Graham when we met with him that he wants everything insulated so the parts aren't sticking out. So he wants covers, so that can also help as well.
And one question from the decision matrix, you put the weight based on the efficiency. How did you quantify the efficiency for different designs?
By using the equations. We didn't really show, but we had a whole spreadsheet set up where we would input the values based on the different lengths and where we'd be experimentally testing them. And we had the equations in the spreadsheet, and they were popping out coefficient of friction numbers theoretically. So we used those because we thought our test would be pretty representative and close to the theoretical calculations.
Can you briefly explain how the solenoid works to help control the brake?
From our understanding and brief talks about it, and what was in the prior report is once it hits, I guess I can show it right now. believe there's a sensor here and then back here, and once it hits like a certain angle, and I believe that's 50 something degrees, then it'll lock. It'll activate the solenoid.
If you activate the solenoid, will it lock or unlock?
Activate will lock it,
Activate will lock it.
and then yeah.
Yeah, so it just pushes down on the brake, which is gonna prevent motion of the ankle.
Yeah, so it'll essentially go like this, and then it'll lock like that. So it hits that again, then it'll unlock.
All right. How do you evaluate the performance of the new design of the brake system quantitatively? How to decide, okay, your new design for from my understanding, compared to the progress last year, you update your brake system. How do you evaluate the performance of your new system?
We just looked at the prior report, and they said that like what I described before, how only some of the lever arm was touching the drum. Dr. Rizza told us that he can physically see it just sliding across. So we never actually got to see that demonstration, but he said that when it would activate, but then it would still, like, it wasn't producing enough force to actually lock in place. It was still sliding.
Okay, so the performance can be observed by just.
Yeah, it can be observed. Yeah.
Okay, all right.
Comments?
Yeah.
Yeah. So I think just suggestions, comments. I think Dr. Riza mentioned that in your class, eventually if you have all these devices, you can come to our children's, we have Get Lab. So I will help you help the best. As this mentor just asked questions. So once you go through the, force blends, right, you can measure the force, ground direction force. And also we have the markers we can put on your ankle joint to measure your plant flexion and the dorsiflexion. It's just my suggestions. I'm not, saying. So, what do you think?
Oh, I agree with you. I just realized that you're missing that. Well, sorry, I missed that one too. Not doing too well this week. But I missed, you should have a test 9, which is a validation. That's what I think we talked about.
Yeah.
Using this facility. So we'll add that. I think we'll.
Don't worry. Everything free.
Just kidding.
No charge.
I think monitoring, give ask good questions. Very good questions.
All right, let's thank this group for their great work. Yeah, the last group can get prepared.
Yes.
You can get started when you're ready.
Welcome to our presentation. My name is Rachel Planky. I'm Cohen Whiteman.
And I'm Brian Cox.
And this is our design proposal for the new helmet to treat plagiocephaly.
To start out with the problem statement, the goal of the project is to improve on the contemporary brace design for plagiocephaly helmets currently. And there's 2 main ways we decided to do this, which is by reducing the weight and improving breathability. These are the main 2 factors of concern because obviously we're working with infants, and the most important thing is that they wear the helmet. So if the helmet is too heavy, it's too uncomfortable, it gets too hot, they don't realize that they need to wear the helmet. They're just going to take it off. So it's our plan to improve the helmets as best as possible, to aid that To help fabricate the helmets, selective laser sintering, also known as SLS technology, will be utilized. And it reduces the time and specialization needed to help create one of these helmets. And to help remove weight and increase breathability, a lattice structure will be implemented into the design.
So getting into the background research, we're going to start with our design objectives and constraints. First is the objectives. Our most important one is weight, and this is just reducing the weight of the helmet in comparable to other ones on the market. Along with this goes breathability, and we were looking at lattice or wool patterns to increase the breathability of the helmet. The third is the bivalve style, which just means that as opposed to opening on the side of the head, it opens on the top of the head, which was preferable to the side style just based on recommendations from Dr. Liu and also just what we see in the market currently. The ease of use is also important as this helmet does need to be taken on and off every day as it's worn for about 23 hours during the day and then 1 hour off. So we just wanted to make sure that it's easy to use for parents. The lattice density was also a concern, and this is informed by FEA results, but basically this just means how dense the lattice cells are. So objectively, less dense lattice is more spread out, and then more dense lattice is more condensed. And so that is just informed by FEA, and basically our goal with that is to maintain the structural integrity of the helmet while also maintaining breathability. And then the patient geometry, which informs the helmet size and also where the forces are on the helmet. So this is derived from 3D scans of the patient's head. And getting into our design constraints, the first one is biocompatibility. So this has to do with the material used, and we wanted it to be biocompatible and also comfortable on an infant's head as their skin is more sensitive, so it's more likely to be susceptible to irritation from harsh materials. We also want the cost of the helmet to be less than $2,000 to be marketable and competitive compared to some other helmets that are already out there. The print time was also something of concern. We wanted this to be less than 48 hours, as a lot of existing helmets have print times or have turnaround times that are from 1 to 2 weeks, which isn't ideal if you really want to get this, disorder treated in a timely manner. And from calculations using the Pudsley method, we determined the factor of safety had to be 1.6, just based on the factors A through E that we looked at. And then the size of the print has to be within the constraints of a 3D printing platform. For us, that was through the MSOE Rapid Prototyping Center. So we use those constraints to inform the size of our brace or helmet. And then this would also be something to consider in future manufacturing. So getting a little bit in the condition, it's called plagiocephaly. It's also called flathead syndrome. And it is usually attributed to long periods of external pressure on one side of the head, usually from laying down or just not enough tummy time as a child. The first treatment for this is usually physical therapy, and then if this doesn't work, they move on to a cranial helmet. So some cranial helmets out there, the first one is the first FDA approved helmet, which is the Doc Band. This one has a side open design, as can be seen in the picture, meaning it just opens on the side. This one is a lot more open, has an open top, and it's comparable to the next one, which is the Star Band, which was the second FDA approved helmet. They have about 7 designs here, but as opposed to the Doc Band, this one uses passive correction, which means that it allows the head to grow into spaces as opposed to applying pressure onto the head to fix the deformed skull areas. The third one is the Boston Orthotics Boston Band, which is a side open design and claims to have a quicker treatment of about 10 to 14 weeks, as opposed to the 3 weeks to 6 months that is usually required of these helmets. And this one also claims to have less follow-up appointments, just making it an overall better design. But all of these have about a turnaround time of 2 weeks from the first scan to when you get the helmet back. So there is obviously room for improvement there.
All right, so to get into the methods of manufacturing, for this project, we're using additive manufacturing, which is just a process of building the part layer by layer. So material is deposited and fused together one layer in one plane, and it'll step up and go to the next plane. And then compared to typical manufacturing styles like subtractive manufacturing, or even for like other braces or plagiocephaly helmets, they'll thermal mold with plastics. This is a little bit more robust and can lead to more complicated designs. It requires less specialization on the fabricator's part as well. And then a variety of materials can be used, such as polypropylene, polyamides like nylon, or polyurethanes like TPU.
So in terms of the materials used in these devices, biocompatibility is the first and foremost requirement for any material used in a medical device and is a design constraint for this project, as previously mentioned. Biocompatibility basically means that the material is suitable for use on living tissue and has no adverse effects on human health. Polypropylene and thermoplastic polyurethane are versatile biocompatible polymers that are used in various medical applications, including 3D printed orthotics. Orthotics utilize polymers in various ways, various parts of their design, such as the hard outer shell, as you can see in the image in the top right, as well as the inner foam liner of the device. TPU has been used in newly developed engineered foam composed of lattice structures, similar to the image in the bottom right there. These reduce the weight of the material while maintaining the stiffness and strength, but also improve the breathability and airflow of the foam, which increases the patient comfort, therefore increasing the patient compliance with the device and therefore the effectiveness of the treatment. Previous senior design groups have done a lot of work with polypropylene, creating braces and helmets. This has included research, 3D printing, design, and testing. And based on that work, it has been selected as the primary material for our project.
So getting into the preliminary work that we did, the first was the factor of safety, which was taken from the previous design group. And basically what this is it has factors A through E, with factors A through D being scored on a, or factors A through C being scored on a scale of very good to just good, or very good to poor. And so basically you assign a value to these different variables. On the bottom, you can't really see the small text, but it lists what every factor means. And then factors D through E are classified from very serious to not serious. And so this kind of lists out where we placed all those values, and then this summed to a factor of safety of 1.6 using the equation in the front. So part of our process was using a scoliosis brace from a group last year to inform our development of lattice technique that we wanted for the cranial helmet. And this was used because the previous design had a similar purpose for correcting a condition. And so it made it a good match for this project to basically test out different types of lattice integration using the brace's existing data. And the outcomes of this is that we learned about the manufacturability, the limits, and the comfort that apply to the cranial helmet as seen through the brace. We also developed a feasible method for adding these lattice sections by testing them on the brace. And then because of this, we enter next semester with a clear approach for the helmet design that really will cut down on the amount of testing and experimentation we have to do in Creo and other such softwares.
So to analyze the material properties of the brace under load, a static structural study was done in ANSYS. Specifically, we used shell elements just due to the shape of the brace because it's so much thinner than it is tall and wide. So we can estimate that it is 2D. So the model was constructed from a 3D scan of the patient and points and generated points, and curves were created from those points, and those curves are lofted together to help create the brace, in which then a step file was constructed and put into ANSYS. And then before analyzing the brace as well, there needs to be a few things done in ANSYS space claim to make sure that the software can actually identify what is happening. So the material should be a surface, not a solid body. And then also the area where the pressure band and the strap forces is projected onto the brace. So as you can see here, that like square section area is about like 4 inches in length. That is where the corrective pressure force is applied to the back. And then on these little circles here, there's 2 forces going each way to represent the strap forces. And then at the very bottom here, sitting at the hips, is where the supports were added as well. Initially, they were fully fixed, and then they were switched to be displacement supports as well. To generate the mesh, it was set to be 75 millimeters. This was a good enough size to have some variability in the stress results, but it also didn't take too long to generate. However, there were some issues when actually resolving the stress due to the supports. There are a few solutions that are being looked into, including compression-only supports or chambering where the supports are applied. But this is something that we're looking forward to in the next semester to move on with.
Next into the CAD modeling of the brace, it was primarily done in Creo, and we quickly found out that Creo's lattice tool could not be used on curved surfaces. It would only work on planar surfaces. So this led to a couple ideas of separating the lattice from the brace basically. And so the first idea was to glue lattice pieces into windows, but this posed obvious comfort and safety concerns, as the lattice would be directly in contact with the skin, which could lead to irritability if the material was abrasive. And then the second and final idea that we had were outward facing C channels as shown in that picture there. And this would hold removable lattice inserts without touching the patient's skin, which allowed for switching out of lattice samples, as well as just overall safety and comfort provided in these C channels. Along with this, we printed several lattice samples with different cell sizes to compare the densities just by visually looking at them. But the final choice will be based on FEA results to maintain the structural integrity of the brace in the end.
So using these brace CAD models created in Creo, we went ahead and begun the prototyping process early in the semester. So we printed the braces in polypropylene with the SLS machine at MSU's Rapid Prototyping Center. It took about 50 hours per brace, an hour of setup, 24 hours of printing time, 24 hours of cooling time, and then about an hour of post-processing. And from that, we were able to create 7 prototypes throughout the term. Starting with the first design that we came up with, known as Prototype 1. This design, as you can see, features 3 large windows, a very large one in the front and then 2 narrower ones on the sides to essentially test how large the windows could be feasibly made and printed. But as you can see, the first print shown on the left had significant fusion failure, and the second print on the right was slightly better. It was still not successful. This is because there can be a lot of issues printing polypropylene with SLS. It can be very sensitive. So in an attempt to improve upon this, we examined the SLS settings within the software at RPC, and we were able to get 2 successful prints. The first successful print shown on the left and the second successful print shown on the right there, utilizing the following settings here. So laser power of 25 watts, scan spacing of 0.007, a bed temperature of 141 degrees Celsius for the first print on the left and 135 degrees Celsius for the second print on the right. Additionally, we added a rotation of 25 degrees for the second print in the SLS software. And based on the second print's higher quality and better scaling to the CAD model, we decided to go with the second successful print settings for the following prototypes thereafter. So getting into the second prototype, the second design, this features 3 smaller windows only in the frontal plane of the brace. They're horizontal and they feature the C channel that was modeled in CAD. But upon printing this, we noticed that there were gaps present in the surface of the brace all around the circumference of the C channels. which were deformable. It felt as if they could be pushed out of the brace, which was a significant issue that we wanted to resolve. So in an attempt to improve upon this issue, we created the third design known as Prototype 3. This now featured a vertical window in the middle to hopefully capture less of the curvature and ideally improve upon the gap issues, which it did. As you can see, there are less gaps in the image on the right, but they were still present. So with the gap issues not resolved, we had to dive deeper to understand why this was happening in hopes to resolve this issue. So we examined the STL of the CAD file. The STL mesh was modified to be made smaller by adjusting the chord height of the mesh. This more accurately captured the geometry of the brace, especially around those C channels for the SLS software and printer. And this successfully printed the C channels. As you can see there were no gaps present with this print of Prototype 3, the successful one, and the 7th print overall. And then finally, we printed the 4 flat sheets of lattices, varying the cell sizes, but keeping the octahedral lattice cell geometry constant. So the Z dimension of 2 millimeters thick was kept constant, and then the X and Y sizes were varied for each lattice to create varying densities, as you can see in the image on the left there. Letter A is 16 by 16 millimeters, so that's the X and Y dimensions. B is 14 by 14, C is 12 by 12, and D is 10 by 10. These lattices were printed in polypropylene. They were very flexible, but still retained their strength and stiffness. They all printed successfully on the first try, and no powder evacuation was observed, which is a common issue with SLS printing in polypropylene. And with these 7 prototypes, we learned a lot about the capabilities of prototyping at RPC, the SLS printer, polypropylene, and working through the issues that we ran into to get a successful print. And these lessons learned, especially the STL mesh settings, will be applied to the helmet manufacturing process in the spring. So now getting into the design concepts for the actual helmet. The first design concept is a bivalve style helmet that features a traditional toggle latch on both sides of the helmet. Basic operation of this helmet involves flipping the lever over to the front half, allowing the loop to catch onto the hook and the catch plate in the front half of the helmet, securing it in place and closing the helmet. This can be 3D printed as part of the helmet, but some bigger feasibility challenges would be ensuring that the forces from this mechanism are enough to close the helmet and apply the forces needed for successful correction and treatment of the condition, which would require significant work in the spring semester.
The next one was the over center toggle latch and hinge. And this was a side open design with a hinge on one side and then a over center toggle latch on the other. And for this hinge, it could either be a print in place, meaning that it would be completely modeled in CAD and then printed, but this would be sensitive to printer tolerances. The other way it could be done is with a traditional hinge, and this would just be hardware that would be bought. But this would require post-processing and have an added cost. And the latch itself uses an elastic strap and a hinge clip to pull both halves together. And the elastic strap would be added in post-processing, so this would add another cost, albeit small, but it would be something to think about in the larger scheme of things if this were to be manufactured widely.
And for the third design concept, it's very similar to the first one, except with traditional latch, we're using cantilever beams to help latch it together. So there's 3 cantilever beams as seen there, offset by each other. So when the user closes the helmet, the beams are pressed down against each other and held together through compression and friction. And then there will also be a notch at the top to help them lock in place. So hopefully it works as though you just press down and it will lock in place, and it'll pick it out and press down as well. This is effective as it is able to be printed all in one on SLS, but there would definitely need to be FEA run to see if these beams are strong enough to bolt together and if they'll break under load. And then there's also a traditional hinge on top, which uses fasteners to help close the bivalve.
So then the first task of the spring semester will be to evaluate each of these design concepts and select one to develop. Additionally, we would like to test polypropylene lattice samples in 3-point bending to understand their mechanical properties as part of our project. But then from there, we will follow the design process that we developed using the scoliosis brace this semester to streamline the work that will be done on the helmet next semester. Then we will finish the term with design validation and testing using the orthotic testing fixture and preparing our final design report and presentation. And with that being said, that concludes our design proposal for the cranial helmet. We'd like to thank everyone here today for their time and extend a special thank you to Dr. Liu of Children's Wisconsin and the Medical College of Wisconsin. And we will now open it up to any questions that you might have. Thank you.
Questions?
Yeah.
So, hold on. Give me 5 seconds. All right, so you're in the real application of this, you're scanning the child's head to create the helmet, right? So how do you make these, how do you make your like official final product design repeatable then, since it's like bespoke every single time?
Basically, so there's not like a orthotic that's like you just kind of, it's automatic. Basically, everyone has, it has to be specific to the patient, just based on their needs too, because some deformation could be like the side of the head, another kid could have deformation on the back of the head. So it has to kind of be curated to the patient anyway. What the scans do is kind of tell you where that is needed. And then also like that would determine, you know, how the helmet is just based on where the pressure has to be to move the head into the position that you want. That's not really what we're focused on. We're focused more on like the breathability and like the lattice design of it. That would be kind of more of an orthosist job, which would be kind of like outside the realm of what we are trying to accomplish in this.
So your like final design would be like, this is how we achieve more breathability.
So this is just for like one specific kid's geometry. Same with the brace. It was just modeled based off of a single patient geometry. Their goal was similar to ours. So not kind of like an all around solution to like treat this disorder in general. Since every case is specific, it has to be specific for every patient.
And the patient's geometry is scanned. They generate a 3D scan of the patient's geometry, and then that is converted into these like curves that are put into the CAD model, and then you generate the brace from there utilizing the patient curves. So that's how they actually make it custom for each patient.
It's more so because like typically sort of like orthotics and just like stuff and scoliosis in general, like it's always going to be patient specific. So we're more focused on like the process and improving everything in that part, because it's always going to be a like specialized process. Yes, or a specialized thing that like doctors have to be a part of. If you can't like fully manufacture it.
I have a question. For the FE modeling, how you get the material properties? Do you do any mechanical testing?
So later on, we will just for now preliminary, we use an estimate on the Young's modulus for polypropylene because it is nonlinear material.
Yeah.
But later on, we're going to use secant modulus after finding that through testing.
Yes, yeah, that makes sense. Because of the different like 3D printing conditions, it would affect the material properties.
Yeah.
Well done. So one question is, traditionally, orthotists use strap to tie helmet. So in your design, I saw that you use instead of using strap, you use using that locking mechanism. So my question, in your FEM model, how do you take consideration of locking system, which may provide different pressure in for your FEM model?
So there's different types of like forces and loads we can apply Obviously, it wouldn't just be a direct applied force. We would have to investigate further at like which would be best, but probably like a compressive force and then maybe a friction force as well, just due to the nature of how they're connected.
So I'm just thinking in the practice, if you want to develop this locking system, I'm perfect fine. So you might make different scale to lock it. Scale 1, scale 2, scale 3, which provide different force. That then your FEM model can assess this variety of this, pressure. So that's just my suggestion, because in the practical, authorities just using their hands to tie it.
Yeah.
Right, because that's on the strip.
Yep.
So I think this is just my suggestion.
Thank you.
Maybe I have one question. It's similar to the last one I asked. What kind of data eventually you will collect to evaluate the performance of the new design?
So we will run the FE analysis to get the stress results and see where the lowest stress areas are. And then Dr. Rizza currently has some design equations, which we can feed our stress results in to help generate the relative density of the lattice that will be utilized, such that it still has comparable material properties, but it also maximizes the breathability at that point. So I guess converting the stress to the relative density is the main data.
Stress to relative density. So the relative density is what you're eventually looking for.
Yeah, the relative density of the lattice structure.
All right, thank you. Any other questions? Great. Thank you so much. I think that's the end of this session. So the next session will start from 10:30, and there's another session starting from 1:30 p.m. in the afternoon. So you're welcome to go to whatever sessions eventually end. All right, yeah, thank you so much for your time.
Everybody else had very similar.
Yeah, medical stuff.
I missed it, sorry.
The projects are pretty cool.
Yeah. Kind of nice.